Hello, ladies and gentlemen. How are you?
Hi.
Shankar.
Hi, Ashok.
How are you?
Good, good.
Uh,
What is the temperature there?
it is about 18, 19 degree.
Wow, good.
So all the friends are here. So I am in my daughter's place in Arnhem.
Okay, okay.
Oh, Takuo. Hello, how are you, Takuo? Are
You are
you
on
coming
mute.
to Bhubaneswar, Takuo? Your sound is not working, Takuo.
You are on mute. Tako.
Mute.
You have to unmute.
Unmute, Takuo.
Oh, can you hear
Hello,
me?
Takuo.
Hi,
Yes, I
hello.
can hear you.
Nice to see you again.
Yes. So, are you coming to Bhubaneswar?
Yes, next October.
Yeah.
Yeah, I'm
Not next
preparing.
October, this year's October.
Yeah.
So, we will wait for your paper and abstract.
Yes, I'm preparing my abstract, and I will send
Okay.
you by the
Yeah.
deadline.
So, our expert Shankar will also be there. Everybody will be there.
Yeah, I hope.
And I can see Kurt is there. Okay. He's always participating. And one more friend from Ghana, I think. Samuel, are you coming to our India conference?
Yes, please. I'll come in October.
Oh, excellent.
Yeah.
So please let us know your program. And if you want to present something about your smelter of Ghana, you are welcome.
Okay. All right. Sure.
Okay. So we will start in another 3 minutes. Oh, Kurt, everything fine? Kurt from USA. No, your speaker is not there.
Ashok, at Belgaum also it is about 20 degrees now.
Wow.
And because it is raining.
Okay. Because Nagpur is burning 40 degrees centigrade, 42, 43.
Yeah.
So a few days, I will be back on 1st May.
Okay.
Oh, Manta has joined. Very good.
Good afternoon. Still can't hear anybody.
Yeah.
So we'll start in 2 minutes. Now there are two Priyankas. One Priyanka from JNRDDC, one Dr. Priyanka from JNRDDC and IBAAS Priyanka.
Hi, Kapuri. You are on
Dr.
mute.
Kapuri is there.
Kapuri, you are on mute.
Hi, good afternoon.
Hey, good afternoon.
Oh, Dr. Kapuri, how are you?
I am fine. How are you?
Yeah, we'll wait for you in Bhubaneswar conference.
I'll try.
Okay, please.
Nitin Patel has joined.
Oh, Nitin Patel has joined. Our friend Nitin is here. Good.
Hello.
Hello.
Hello, Nitin. You have
Hello.
forgotten us.
No, I have not forgotten.
So you will be there in Bhubaneswar conference, Nitin?
Uh,
Please try to be there.
I can't hear anything.
Bukela people have also joined. Timo Dobler, Nitin Patel. Okay.
Hello, everybody.
Hello,
yeah,
everybody.
conference.
Hello, everybody.
Yeah.
Anand Sonkar. So Bukela, we invite you in India conference in October. Okay, this is the time.
Kurt has raised his hand.
Yes. Good afternoon, ladies and gentlemen. Please,
can't hear
audio.
anything.
Please switch off your
hear.
audio. Please switch off your audio. So, good afternoon, ladies and gentlemen. Today we have Dr. Priyanka Nayar from JNRDDC, Aluminium R&D Center. She will speak on high purity alumina. She is PhD from in physics, and she worked in China also as postdoctoral research fellow in Nanjing University. So I will welcome Priyanka Nayar and Dr. Priyanka. And now we will run the recorded presentation. It is about 57 minutes. Oh, you can see Priyanka Nayar, Dr. Priyanka Nayar, JNRDDC Nagpur. So this will be about 57 minutes, 1 year presentation on high purity alumina. And after this, there will be a questions answer session, and you may continue as long as you want your question, as long as your questions are there. So I am switching off, and Priyanka of IBAAS office will run the presentation. Thank you.
A very good afternoon to one and all. Let me first thank Dr. Nandi for giving me this opportunity to present my work in this prestigious IBAAS 2025 technical lecture series. Today I am going to speak on 4N HPA, its science, strategy, and scale. Material at the crossroads of innovation. Before starting my presentation, let me first introduce myself and my institute. I'm Dr. Priyanka Nayar, and I'm working as a scientist in JNARDDC Nagpur since 2016. Basically, I'm a physicist. I've completed my PhD in physics from Amritsar, Punjab, and my postdoctorate from Nanjing University, China. My research interests are alumina thin films, alumina coatings, alumina nanomaterials, and recently I have started working on high purity alumina, specifically on 3N and 4N high pure alumina. About my affiliation, Jawaharlal Nehru Aluminium Research Development and Design Center. It's an autonomous body, a premium R&D institute under Ministry of Mines, Government of India, and it is dedicated to advancing the aluminium sector through its research, process development, and analytical support.
Here.
With state-of-the-art facilities and domain expertise, JNARDDC bridges the gap between industry needs and scientific innovation. Before starting my presentation, I'll introduce you with the contents of today's presentation. First, I'll give you the introduction and objective of my PPT. Then I'll introduce you all with high purity alumina, specifically the 4N HPA. Then I'll let you know why purity is so much important for some specific applications. HPA forms and their uses. HPA's global demand and its applications. HPA's current production technologies, its industrial value chain and market landscape. Then I'll talk about its key players and the cost benchmarks. Eventually, I'll explain some work which I have done on HPA at our institute, JNARDDC Nagpur. Then I'll let you know how to go from lab success to bench scale. And finally, I'll talk about some key takeaways and the road ahead. So first is the introduction and objective. What actually is high purity alumina? High purity alumina, specifically 4N, which is 99.99 pure, has emerged as a critical raw material enabling modern technologies. Its unique chemical stability, optical transparency, and high thermal resistance make it indispensable in LED phosphors, lithium-ion batteries as separators, and semiconductor substrates. As global industries transition towards electrification, energy efficiency, and smart electronics, the demand for foreign HPA is rising rapidly. However, the supply chain remains narrow, capital intensive, and largely dominated by only a few players outside India. So, the major objective of my today's presentation will be introduce the science behind 4-NHPA, its key properties and applications, to highlight the strategic and economic importance of developing domestic capability, to explore how investors and industry can leverage emerging opportunities, and to present the R&D efforts and breakthroughs achieved at JNARDDC, including a lab-scale validated process for producing foreign HPA. So this slide, the high purity alumina foreign HPA, this slide present two key visuals. If you can see, you can see two visuals. First, we have a bar chart that compares different grades of alumina based on their purity levels. As we move from metallurgical grade to foreign HPA, there is a clear and dramatic reduction in impurity content. So this trend is crucial because applications like LEDs, lithium-ion batteries, and semiconductors demand extremely low levels of contaminants. And the second image on the right side, the second table, in fact, it's a periodic table where we have highlighted the most critical impurities, specifically the iron, silicon, and sodium. So these elements, even in parts per million, if present in ppm concentration, that can severely affect the performance and reliability of the final product. So like if we talk about iron, so what iron can do, iron can introduce unwanted color and reduce electrical insulation and making it a problem for its use in optical and electronic applications. If we talk about silicon, it can interfere with crystal growth and it will potentially causing defects in sapphire substrates. And finally, if sodium is present even in ppm level, it's a mobile ion, and in some applications related to electronics, it will cause electrical leakage or instability over time. So in short, we can say if metallurgical grade alumina contain iron and silicon well above, I think 100 ppm, in foreign pure alumina, we aim to keep them below 10 ppm and even lower if sodium is present. We ideally think of less than 5 ppm. So achieving and maintaining this level of purity is what enables high performance materials like transparent sapphire, high strength wafers, and safe, stable battery components. And this is where our synthesis approach at JNARDDC is making a real difference. And that work I'll explain later in this PPT. Now next is why purity matters. So let's discuss the physical and chemical properties of high purity alumina and how achieving these purities, properties are critical for HPA performance in some specific applications. Like first is its high melting point. As we all know, alumina's melting point is very high, that is 2050 degrees Celsius. So HPA has an exceptionally high melting point. That makes it suitable for use in extreme environments, such as high temperature industrial applications and electronics. This property also ensures the material can withstand harsh conditions without any degradation. Second is its excellent hardness and chemical stability. So HPA is highly resistant to wear and corrosion, which is very much essential for applications where durability is crucial, like in cutting tools or components which are exposed to aggressive chemicals. Third property is high dielectric strength and thermal conductivity. So HPA's high dielectric strength makes it an ideal insulator, while its high thermal conductivity that allow it to effectively dissipate heat. This makes it indispensable in electronic and electrical devices, including high performance semiconductors and LEDs. And next property is transparency to visible and infrared light, especially when HPA is in a sapphire form. Forms I'll discuss later, but just to mention, HPA when processed into sapphire form, it becomes transparent to both visible and infrared light. This unique property allows it to be used in optical applications such as lenses, windows for high-tech devices, and even certain medical instruments. And last but not the least, its inert and non-reactive nature. So HPA's inert nature means obviously it doesn't react with other substances, even under harsh conditions, which makes it ideal for applications specifically in the aerospace, automotive, and electronic industries where the stability is very much required. Next is HPA forms and their uses. So now let's take a look at the different forms of high purity alumina and how each form is utilized in various industries. So first is the powdered HPA. This form is widely used in some specific applications like ceramics, where it provides enhanced hardness and durability. It's also crucial for battery separators that helps to improve the performance of rechargeable batteries, and for the phosphors, which are very much useful in display technologies and lighting applications. Second is the granular HPA. In its granular form, it is used to create sintered components that are part of advanced materials, as well as crucibles that are essential for high temperature processing. Granular HPA ensures the necessary properties such as its high thermal stability and resistance to chemical attack for some demanding applications. And finally, in the sapphire form. Sapphire form is actually a single crystal form. When alumina is in its single crystal form, we call it sapphire. So this is one of the most well-known form of HPA. And in the sapphire form, it is used in high precision applications, such as LED substrates, watch crystals, and optical windows. Sapphire's unique properties, such as high transparency, strength, and resistance to scratch, it makes it ideal for these high-tech applications. So producing sapphire requires ultra-high pure alumina, which should be greater than equal to 4N, means it should be minimum 4N, and then it can be 5N or 6N as the feedstock material. So it will underscore the importance of achieving extremely high levels of purity. Next is the global demand and its application. So first, we'll discuss about the HPA use in LED phosphors. High purity alumina plays a crucial role in the production of LED phosphors, which are responsible for the color and brightness of LED lights. So in this particular application, HPA enhances the efficiency and longevity of LEDs by contributing to improved color and higher brightness output. So as the global shift towards energy efficient lighting continues, the demand for LED lighting has increased. So this in turn increases the demand for HPA, as it's very much integral in manufacturing phosphors that are used in white and colored LEDs. The growing trend in both residential and commercial sectors to replace traditional lighting with LEDs will fuel this demand. So in the upcoming years, as energy saving technologies gain more traction worldwide, particularly in the context of environmental regulations and green building standards, the use of HPA in LED phosphors is expected to see substantial growth. Next is HPA's use or application for lithium-ion batteries as a separator. So moving on the lithium-ion battery separators, high purity alumina is increasingly used in this critical component of batteries, that is the separator, which is used particularly for electric vehicles and portable electronics. HPA is used to enhance the separator's thermal stability, mechanical strength, and chemical resistance, which are the key factors in improving the safety and performance of lithium-ion batteries. You can see the image below. Role of these separators is to prevent the short circuit within the battery. It actually separates the anode and the cathode while allowing the flow of ions. So with the growing demand for EVs, as we know, the demand for EV is very much increasing. So with the growing demand of EVs and renewable energy storage solutions, the need for better, safer, and longer lasting batteries has driven up the demand for HPA in these separators. So as the electric vehicle market expands and the push for more energy efficient and long lasting batteries intensifies, we can expect a significant increase in the demand for high purity alumina for its use in lithium ion batteries as a separator in the upcoming years. So next is HPA's use for sapphire substrates. High purity alumina is actually the starting point for making a sapphire substrate, which are used a lot in LEDs and semiconductors. So what makes it so special is its high purity. Even a tiny amount of impurities, like as I've talked about it earlier, if a tiny amount of impurities like iron or silica or sodium is present, that can affect how the sapphire crystal forms. So we need 4N purity or even high pure alumina, 5N or 6N for making the sapphire. So the process basically starts by heating this HPA to a very high temperature, more than 2000 degrees Celsius, until it melts. Then the crystal is slowly grown using controlled techniques. Like in our work, we have used the float zone technique, which obviously I'll explain later, and which is very clean and avoids contamination. So things like the temperature, pressure, and the speed at which we pull the crystal has to be maintained. Otherwise, defects can form and that will ruin the quality of the sapphire substrate. So once the crystal is formed, it's sliced into thin wafers. These are then used as the base for growing materials like gallium nitride in LEDs or in other high-end electronics. Just to highlight, most white and blue LEDs that we see around us today are actually built on these sapphire wafers, which we normally use in festivals that are actually built on these sapphire wafers. So they are also used in smartphone chips, optical windows, and even watch covers. So high purity alumina, if we say, it's not just a material, it's what enables a lot of the tech we rely on today. Next is the HPA for semiconductor and optical applications. As we all know, electronic devices are getting smaller and more powerful. But one big challenge that comes with this is heat. When semiconductors shrink, they pack in more transistors, which means they generate more heat in a tiny space. And that heat needs to go somewhere. So traditionally, materials like epoxy resins are used to package and protect the semiconductors. But nowadays, these resins are reaching their limit. They just can't keep up with the thermal demands anymore. So one way to deal with this is by mixing thermally conductive fillers into the resins. That will help to draw the heat away from the chip and reduces the risk of failure. Some of the fillers that are being used are crystalline silica, magnesium oxide, and of course, this high purity alumina. And out of all these, the high purity alumina is the preferable one. HPA has almost around 7 times a higher thermal conductivity compared to silica. And it also expands 50% less with heat. So that is important because less expansion means less mechanical stress on the device. That is why HPA is becoming a preferred material for thermal management, especially in high performance electronics, where even a small temperature difference can affect the performance of the device. So overall, we can say HPA is not just important for sapphire substrate or LEDs. It also plays a key role in managing heat in advanced chips and devices. So next is current HPA production technologies. Several methods have been developed to produce HPA, and each has its own advantages and challenges. The main technologies include like Baer process, which is a very traditional alumina route. Another is the alkoxide route, and the third is the hydrothermal or leaching kind of route. So I'll explain one by one. First is the Baer process, which is the traditional alumina route. So Baer process, as we all know, it is the most widely used method for extracting alumina from bauxite, and it has been in use for over a century. This process is the foundation for most alumina production worldwide, particularly for conventional alumina production. So what happens in this process? All we know, first bauxite is crushed and ground to a fine powder. Then it is mixed with a hot concentrated solution of sodium hydroxide, which causes the alumina in the bauxite to dissolve, forming sodium aluminate. While the impurities such as iron oxides that are left behind as a residue, which we commonly known as red mud. And the solution is then cooled and alumina is precipitated out of the solution by seeding it with aluminium hydroxide crystals. This results in crude alumina, which is separated, washed, and then subjected to calcination, where it is heated to high temperature to remove the water and convert it into high purity alumina. So the Baer process is highly mature with well-established infrastructure globally, and it is capable of large-scale production, but it does have some challenges. Like it is highly energy intensive, especially during the calcination step that required significant amount of heat. Additionally, it generates a substantial amount of red mud, which is an environmental concern due to its large volume and capacity. Another limitation is that while this process efficiently produces alumina, purity level is generally not sufficient for high purity applications, such as semiconductors or LEDs. So to produce high purity alumina, we have to use some further steps, such as some additional refining and purification processes, which are very much necessary. So in summary, while the Baer process is highly effective for large-scale alumina production, it's not ideally suited for the production of high purity alumina due to its energy demands and the need for additional purification steps. Next is alkoxide method, which I have used in JNARDDC to produce high purity alumina. So this alkoxide method is a chemical route to produce ultra high purity alumina. And it is not starting from the bauxite, but it is starting from the pure aluminium metal. So this process is particularly suitable when our end goal is to obtain 99.99 or even high pure alumina, which is required in LEDs, semiconductors, and sapphire substrates. So let me walk you through the main steps of this process. We can see the flow chart on the right side. So first, the high pure aluminium metal is reacted with an alcohol. Commonly, we use isopropanol in a controlled environment. So this forms a chemical compound which is called aluminium isopropoxide, which is a type of alkoxide. So this reaction is highly sensitive and it must be carried out under moisture-free inert conditions to avoid the contamination. Next, the aluminium oxide is purified through vacuum distillation or solvent extraction. This step is very much critical to remove metallic impurities like iron, silicon, and transition metals, if any, which can affect the optical and electrical properties of the final products. So once we purify, then the alkoxide goes under hydrolysis process. It means it will react with water to form the aluminium hydroxide. And then this is followed by calcination, where the hydroxide is heated at high temperature. above around 1000 degrees Celsius to yield high purity alumina. So now what makes this process attractive is its ability to produce very pure alumina with tight control over contamination, and it's also flexible. We can tailor the process parameters, or we can optimize the process parameters depending on the required particle size, phase, or morphology. But there are some challenges in this process also. Like this process is also relatively expensive. Because it uses your aluminium metal or high purity reagents. Next, it also requires careful control at each step, particularly distillation and hydrolysis step, to ensure the desired property. And while it's excellent for specialty applications, it's not as easily scalable as the Beers process. So in summary, we can say the alkoxide route is highly suitable when purity is the priority, especially in critical electronics and optical applications. However, the trade-off is the higher cost and the complexity of the process. The next route I'll discuss is the hydrothermal and hydrochloric acid leaching method. So this slide will illustrate the hydrothermal and hydrochloric acid leaching route for producing high purity alumina. We start with raw materials like bauxite or kaolin or other aluminium bearing ore. These are first ground to a fine powder to increase the surface area and improve the leaching efficiency, because we have to do the hydrochloric acid leaching. So the powdered material is then subjected to leaching using the HCl under controlled temperature and pressure conditions. This is either done at atmospheric pressure or in hydrothermal reactors. So this step dissolves the aluminium content into the solution, leaving behind most of the impurities as the residue. Next, the leachate is filtered to separate solids from the acidic aluminium containing solution. The solution undergoes purification using techniques like solvent extraction or ion exchange to remove the trace impurities such as iron, titanium, silica, etc. So once it is purified, aluminium hydroxide is precipitated from the solution. And this step is typically achieved by adjusting the pH or adding a precipitating agent. Finally, the precipitated aluminium hydroxide is calcined at high temperature, usually above 1000 degrees Celsius, to obtain the high pure alumina. The major advantage of this process is its flexibility to work with various low-grade ores and its potential to operate at a relatively lower energy input compared to the Beer process. But the use of corrosive acids and complex purification steps that poses the challenges for scale-up and environmental compliance. Next is its industrial value chain and market landscape. So here is the emerging demand and market projections. This slide shows how the global demand for foreign and even high purity HPA is picking up speed. The main reason, there are more and more applications like LED lighting, lithium-ion batteries, optical lenses, and high-end electronics, all of which needs materials with very low impurities, or we can say very high purity. So if we look at the pie chart, which I have shown here, LEDs are still the biggest users of HPA, but lithium-ion batteries are catching up fast. So that is because HPA is used to coat the battery separators, which improves battery life and safety. So that are the very important factors, especially in EVs and energy storage systems. So if we see on the regional side, Asia Pacific is clearly leading, with China and South Korea at the center of LED and semiconductor production. So they're also ramping up battery manufacturing, which adds to the demand. Overall market is expected to grow by more than 15% annually. That's a pretty sharp rise, and it shows how fast this space is evolving, especially when with the push towards green energy and electric vehicles. Now, why this is important for us? Because India has abundant bauxite reserves. If we can develop and scale up purification techniques like the one we have already demonstrated at JNARDDC, although at a lab scale, then we can capture a slice of this growing market. Instead of just exporting raw materials, we can move up the value chain by producing high purity alumina locally, which will also reduce import dependency and help it make in India initiatives. So this demand trend is not just an opportunity, it's clear signal for strategic investment and R&D focus in this area. Next is the strategic overview of the HPA value chain. If we see this chain, this slide will show the entire value chain for high purity alumina, starting from the raw materials to the final applications. So we start right at the beginning with raw materials. Now, raw materials can be an aluminium metal, aluminium hydroxide, or bauxite, depending on the route we choose. Like at JNARDC, we have used aluminium metal for the alkoxide-based process. So starting from the raw materials, once we have the raw material, now we obviously need to purify it. That's where the real challenge is. And also the value comes in. There are different purification techniques like the alkoxide method, acid leaching method, or hydrochloric hydrothermal treatments. The goal here is to remove all those tiny impurities that can affect the performance, especially things like iron, silicon, sodium. After the purification, we get high pure alumina, at least 4N pure grade alumina, which is 99.99 pure. But the process doesn't stop there. We move into what's called the finishing or crystallization stage. This is where we control the final purity, final properties of the powder, like its particle size, shape, and moisture content, depending on what application we are focusing on. Now the high purity alumina is ready for downstream use. And this is where it gets exciting. It goes into some of the most advanced applications, like sapphire substrates for LEDs and semiconductors, ceramic separators in lithium-ion batteries, and even optical components or special coatings. So this value chain is not just a technical flow chart. It actually helps us understand where the opportunities are. So if we look at it from a research perspective, it tells us where to improve the purity and optimize process parameters. From an industry or investor point of view, it shows where the value is added, where you can scale, commercialize, or even create new IP. So in short, we can say understanding this value chain helps us move from raw resource utilization to high-tech manufacturing or applications. And India has great potential to enter this value chain more strongly by developing scalable indigenous technologies. Next is investment opportunities and challenges. So let's talk about the bigger picture, where India stands today in the HPA ecosystems and what it will take for us to become a global player. So first, let's talk about our strengths. This is the SWOT picture. So first we'll talk about our strength. So we already have a solid base of alumina production in the country. And the demand is only going to rise with growing applications in LEDs, electronics, EVs, and semiconductors. Also, we are not short on talent. India has a strong pool of scientists and engineers who can drive innovation in this space. But of course, we also have some challenges or weaknesses, we can say. Right now, access to advanced purification technologies is limited. And setting up large-scale high purity production plants, it required significant capital investment, which will slow us down. If we look at the opportunities, there are quite a few. The domestic market is booming. Government policies like the PLI scheme, Atmanirbhar Bharat, that are pushing for local manufacturing and self-reliance. And there is a clear need to reduce our dependency on imported high-value materials. On the other hand, there are also some threats we can't ignore, especially competition from established global players. There are so many global players which are already very much established. So there is a competition. Then the technological dependence on imports and the stricter environmental regulations around processing. But the good news is we are not starting from zero. The government has already laid a good foundation. With policy support, what we now need is greater R&D investment, collaboration between public institutions and private players, and maybe even international partnerships, especially in areas like single crystal growth, nano coatings, and end-use ceramic applications. So with the right mix of science, strategy, and scale, India can absolutely rise up the value chain. Instead of just importing high purity alumina, we can actually be the country exporting it, supplying materials for global tech supply chains in EVs, aerospace, optics, and much more. So this transition won't just make economic sense. It will give us a strategic autonomy in sectors that are going to shape the future. Next are who are the key players and the cost benchmarks for HPA. So let us now look at the global scene in HPA production. Global market dynamics, players, cost, and competitive edge. So as of now, the market is largely dominated by a few big players. Companies like Altec Chemicals in Australia, Sasol in South Africa, and Sumitomo in Japan. These are well-established firms with decades of experience. They mostly rely on conventional and proven methods like HCl acid leaching, alkoxide process, and thermal decomposition of aluminium salts to produce high purity alumina. Different companies use different production routes. Some go for HCl leaching, some prefer the alkoxide route. And we are even seeing newer players which are using hydrothermal or plasma assisted processes. Each of these methods comes with trade-offs in terms of cost, complexity,